Okay, it's been a while since I can't watch myself doing this. Okay, it's been a while since I made one of these videos, so let's give it a shot. What I want to do is to talk about an introduction to Newton's laws for this little segment. Newton has 3 laws. We need to know them by name. They have the greatest names in the world. Why is this not working? I have to click on this thing. Wow, okay. Okay, let's try again. Take 2. Okay, it's been a while since I made one of these videos, so I'm a little rusty. But what I want to do today is talk about the forces. Yeah. All right, it's been a while since I made one of these videos. We're probably a little rusty. What I want to do today is do a little introduction to Newton's laws. First thing you need to know is that there are 3 of them. You must know them by name. They are Newton's first law, Newton's second law, and Newton's third law. All right, so without further ado, the first law of Newton, the state of motion of an object does not change unless acted upon by an outside force. The state of motion is a fancy way of saying the velocity. Keep in mind that the velocity is a vector. Okay? So we can change not only its magnitude, its speed, we can also change its direction. This is a very qualitative statement. There's no numerics here at all. It's just an object changes its motion if and only if there's a force acting on it. Okay, so the first law is a qualitative statement. The second law, which is what we will be concentrating on greatly, is the net force is equal to mass times acceleration. Net force is written in 2 ways. You can write it as F net, or you can write it as the sum. Right? M is the mass. First time we're actually using the mass. And A is the acceleration. This is a quantitative statement. The second law includes the first law. Okay, so if there is no net force, just looking at the equation, if there is no net force, then the acceleration must be 0. If the net force is 0, the acceleration is 0. Okay, if the acceleration is 0, that must mean that the velocity is constant. Similarly, if the net force is not 0, then the acceleration is necessarily not 0, and the velocity necessarily will change. Okay. Again, this is a quantitative statement. Both the first law and the second law involve a single object. Right? We're talking about the force on an object, the force acting on me right now, the force acting on you right now, the force acting on the ball flying through the air, whatever it happens to be. Newton's third law. I'm sure it's probably more famous of the 3. For every action, there is an equal and opposite reaction. I hit the table, ouch, that hurt. I hit the table hit my hand back. Okay, that's an action-reaction pair, sometimes called an action-reaction pair. But those 2 forces, the force that I hit the table and the table exerts back on my hand, is equal in magnitude and opposite in direction. Okay. All right. So these, again, keep in mind that the vectors, forces are vectors. Generally, we need to look at both the vertical and the horizontal direction separately. This is why we learned how to add vectors in the way that we did, to keep the X and Y separate. All right, just to get the units out of the way, the force units are called newtons. They come from the definition you see on the screen. The net force is mass times acceleration. If you have a 1 kilogram object accelerating at having an acceleration of 1 meter per second squared, it's going to have a net force of 1 kilogram meters per second squared. Okay, that's too much to write for us lazy physicists, so we invented the Newton in honor of Sir Isaac, and is abbreviated as capital N, not lowercase n. It's always capital case N. 1 Newton is defined to be 1 kilogram meter per second squared. Okay. Few rules So I will stop now, put in a couple of play posits to do a couple of easy examples, and then we'll do another one, and then we'll do a third one, finally a fourth one. Okay, so moving on, we're going to skip that one too. All right, some examples of Newton's second law, non-trivial examples. By trivial examples, I mean you have a single mass with a single force having an acceleration that we just saw on the play posit quizzes. Right? If we have a non-trivial example is when we have two forces, say. Right? So here we have, and keep in mind that these forces are vectors. I'm making them very obvious here. I have two forces, one force F1 of 4 newtons, and then force F2 of 2 newtons, acting both towards the right, both acting on a 5 kilogram mass. Okay? I'm not going to bother with the table here because it's just one-dimensional motion, just to keep things a little simpler. All right, so we're going to do a couple of examples of Newton's second laws here. Cut. All right, at this point, I want to do some non-trivial examples. Trivial, I mean, but by trivial, I mean one force acting on a single mass and having a resulting acceleration. Here, I want to have two forces acting, say. On the screen, you have a 5 kilogram mass with two forces, both acting towards the right. One force of 4 newtons, one force of 2 newtons. We have the net force equals mass times acceleration. I'm going to be doing this in a graphical way rather than putting it onto the force chart because it is just one-dimensional motion. Right, so we have two forces acting to the right. Let's say positive is to the right, so we have 4 plus 2 is equal to 5 times A. So you got the naked equation, dress it, as always. 4 plus 2, of course, is 6. That's equal to 5 times A. Solve for A, ta-da. A is equal to 1.2 meters per second squared to the right. The net force is always going to be in the direction of the acceleration. Actually, that probably should have said the other way. The acceleration is always in the direction of the net force, okay? Second example, here we have also the same two forces, but they're actually these are two different forces. They just happen to have the same magnitude. One force is up, the other force is down. When you see problems like this, these are the only forces acting. There's no gravity acting, there's no friction acting. Whatever you see on the screen, that's it. Okay? So we have two forces, one force is up, one force is down. Down here is not necessarily towards the earth, right? This is just down to the bottom of the page. Again, net force equals mass times acceleration. These two forces are in opposite directions, so we're going to be subtracting them. Explicitly here, the positive is upwards and negative is downwards. So 4 minus 2 is equal to 5 times A. 4 minus 2, of course, is 2. So 2 is equal to 5 times A, or A is 0.4 meters per second squared up. So it's going to accelerate upwards. Okay. Just to switch it up a little bit, we have two forces acting to the right, same two forces as before, and I tell you that 2 is the net force. Find the acceleration. Okay. Just a big switch up here. Net force again is equal to mass times acceleration, naked equation. I got my picture on the left there. So sketch, naked equation, dress it, put the numbers in. 4 plus 2 is equal to m times 2. Solve it now for m. M is therefore 3 kilograms. Okay. And finally, if F2 find F2 here, we have an F1 upwards. If the acceleration is 2 meters per squared downwards, so explicitly the acceleration is downwards. Okay, those two forces are in opposite directions, so let's take that into account. Let's stick with the convention of up is positive because the acceleration is negative. It will be negative in the equation. Okay, this is one of the reasons why I always say to choose, if you can, choose the positive in the direction of the acceleration if you know it, to avoid that issue of putting in an incorrect sign. Okay, so net force is mass times acceleration. We have 4 up, F2 down is equal to 5 times negative 2. So 4 minus F2 is equal to minus 10. Ta-da! The force F2 is therefore equal to 14 newtons. Okay, I purposefully made F shorter than F1 visually just to sort of mess with you. The acceleration is down, therefore the length of that F2 vector if I wanted to convey length, the magnitude of the vector. If I wanted to convey the magnitude of the force as the length of the vector, then F2 would have been longer than F1. Okay, so I'm just sort of messing you a little bit there to sort of key you in onto what's happening here. The acceleration is down, therefore the net force must be down, so the down force must be bigger than the up force. Okay. We will break here and do a play pause it, and coming back. All right, welcome back from play pause it. Now we will look at Newton's third law examples. After having done Newton's first law and second law, we will look at Newton's third law examples. Okay, so starting from S, how can we possibly walk forward? Okay, all right, we're from school without walls. Here's a penguin standing on ice. Suppose that ice is really, really, really slippery. How is this penguin going to move forward? Okay, if it's really slippery, the penguin is just going to spin his wheels, so it's just keep trying to move, and he's not going to be able to walk forward. I'm going to zoom in here if I can. Oh, I guess I can't. Oh, there I can. Look at his claw. Look at his feet. He's got claws. Okay, so the claws are going to help him grip. All right. So to be able to walk forward on a slippery surface, we need to be able to get some sort of friction going. If he pushed against the ice and the ice is frictionless, then there will be no friction. All right, so there will be no force pushing him forward. Something has to push the penguin to the left here, okay, or to the right, whichever way he's facing. On my screen, he's going to the left. The penguin's standing on ice. He's not moving. The penguin can't push himself forward. It's like it's trying to lift yourself up, right? You can't do that. Something has to lift you, okay? Something has to push the penguin. What's going to push the penguin forward? The ice is going to push the penguin forward. Why? Because the penguin is going to push on the ice, okay? So somehow you have to arrange for a force to push you forward. You push on the ground. In this case, the penguin grips the ice with his claws, pushes against the ice then pushes the penguin forward, okay? So ice that direction, penguin that direction. The net force on the penguin is therefore to the left here, okay? And the penguin will now accelerate to the left and be able to move, okay? Notice that there are two objects here, okay? The penguin pushes on the ice pushes the penguin. I push on you, you push on me. The bird flaps its wings against the air pushes up on the wings of the bird, okay? So you always need two. So, we go to play pause it for continuation and blah, blah, blah. Let me introduce it. And now for a message from play pause it. All right, welcome back from play pause it. Let's analyze what we had just looked. Oh, not there yet. So let's look a little bit more at what's going on with these action-reaction pairs. We're going to look at two forces, right? Suppose you have this woman standing on the earth. Yes, that is a woman. And let's look a little bit more closely at what's going on here. We need to look at two forces. Remember, action-reaction pair requires two forces, requires two objects. Let's look at a woman, say, standing on the surface of the earth, right? What forces are acting on the woman? You got the weight of the weight is, by the way, the force that is exerted by the earth on in this case, the woman, okay? Which would be downwards. The normal force is the force exerted by the surface, which in this case happens to be the earth. The normal force is the force exerted by a surface on the object to keep the object from going through the surface. So I'm sitting on a stool. If the stool doesn't push up on me, I'm going to go flying through the surface, through the stool itself and into the floor. And if the floor doesn't push up, I'll continue on going through the floor. Okay, that's different than that's different than the force of the earth, right? It's the force of the surface. that keeps you from going through. It's basically the intermolecular attraction between the molecules holding themselves together so you don't slip through and break that bond. Okay. What you see on the screen is not the action-reaction pair. The weight and the normal force are two different forces acting on the woman. There's one object, the woman. There's two different forces that are coming from two different places. The normal force is from the surface and the weight is from the earth, right? The surface is pushing up, the earth is pulling down. Those are both acting on the woman. Those are not action-reaction pairs. The woman is standing there. She's not accelerating. Those two forces happen to be equal and opposite, but that does not make them action-reaction pairs. What does make an action-reaction pair is what we look on here, okay? We need the two objects. What are the two objects? We have the earth pulling down on the woman. That's her weight, all right? So Fe on W, that's the force of the earth acting on the woman. The woman also pulls upwards on the earth, right? The woman, so Fw on earth, that is the force that the woman is exerting on the earth. We will see this later on, but we attract the earth, right? Universal law of gravity, every object that has mass attracts every other object that has mass. The woman has mass, not much compared to the earth, so the woman attracts the earth, right? The earth also attracts the woman. Those two forces are equal and opposite, okay? They are equal and opposite. All right, welcome back from our little video interlude. Oh, I didn't want to see that. Okay, so I'll just come here. All right, well, we're back from the tug of war video that you just saw. What I wanted to do is to go through the analysis a little bit. Dad, and contrary to what the video said and what most people say, Dad did not win because Dad is pulling harder. The implication is always that the stronger person, the person that pulls harder, is going to win. The kids and Dad pulled the same amount. What I have on the screen here are the free body diagrams. I haven't introduced that yet for forces. We will see that, but it's sort of obvious what's going on here. We have a free body diagram. Okay, we have two masses. Each mass is a free body diagram. Right? Free body diagram is a box that you see, and to that box I have attached all the forces that are acting. Now, what forces are acting on the kids? Gravity's pulling down on them. I'm clumping the kids together. Gravity's acting on them. That's W down. The kids are not going through the surface of the earth, so we got the normal force up. Okay? We have the tension in the rope pulling to the right. That's what Dad's doing. Dad's pulling on the rope, which is pulling on the kids. And you have friction because the kids are pushing against the ground. The ground is not frictionless. So the kids are pushing against the ground. They're leaning back, trying to pull Dad toward them. Okay. Dad, on the other hand, has the same four forces: the normal force up, weight down, friction to the right because Dad is digging in. Doesn't have to dig in too hard, but digs into the ground and leading to the right, and is also being pulled by the rope, which is being pulled by the kids. Okay. Now the Dad is obviously heavier than the kids, so the weight of Dad is bigger than the weight of the kids. The normal force of Dad must be equal to the weight of Dad. The normal force of the kids must be equal to the weight of the kids, okay? Because those are the only forces that are acting up and down. Dad is heavier than the kids, so therefore the normal force of Dad is heavier than the kids. It turns out, we haven't seen this yet, it turns out that friction is going to be proportional to the normal force, okay? Since Dad is much heavier, Dad has a bigger normal force than the kids, Dad's going to have the bigger friction force. Dad wins because friction is bigger. The two tension forces there are equal and opposite. Those are action-reaction pairs. Dad pulls on the kids pulls on Dad with the same amount. Okay? So as far as the pull is concerned, it is a tie. All right? Dad wins because he pushed against the ground more than the kids did. Okay, that's the only reason. Generally, all things being equal, generally the heavier person is going to win. Okay, and that's it. Boom. Stop presenting. Stop recording. Make dinner.